In this video, I want to talk about K versus Q. Now, we've actually seen Q before. Q stands for reaction quotient. And what it means is that your system is not at equilibrium. Now, where did we see this? We saw this in electrochem. If you remember the good old Nernst equation, and it sounds like I don't know what I'm saying because my nose is stuffy, but the Nernst equation is when we were trying to figure out an E cell at non-standard conditions. So E cell was equal to E naught cell minus 0.06 over N times the log of Q. So this Q right here is this Q, which is called the reaction quotient. It just means that your system is not at equilibrium. Now, the way that I calculate my Q is the same exact way as I calculate my K. But if you remember us talking about Rice charts at the very beginning, R stands for my reaction, I stands for initial values, C stands for what's changing, and E stands for equilibrium values. These equilibrium values are what I'm plugging in to K because they're at equilibrium. These initial values, on the other hand, are what I plug in for Q. So Q is same expression, products raised to the coefficient over reactants raised to its coefficient, except I plug in initial values for Q, whereas I plug in equilibrium values for K. Now, when do I use this whole K versus Q? When do I use this approach? Well, you use this approach anytime you're trying to predict a direction that the system will shift to reach equilibrium. This is your keyword right here, predicting a shift to reach equilibrium. Because, like I said, Q means we're not at equilibrium yet. We're trying to figure out, well, do we need to keep going to the products to reach equilibrium? Or, because these reactions are reversible, do we need to backtrack? Do we need to start making more reactants in order to reach equilibrium? So this is our approach whenever we're trying to do this. What we're going to do is we're going to solve for Q. Once we solve for Q, we are then going to compare it to our K. Now, if our K, I'm just giving an example here, is equal to 10, and we calculate our Q by setting up our expression using initial values, and our Q ends up being less than K, let's say that our Q is equal to 5. What that means is that our reaction is going to have to keep making products. So it's going to shift to favor the products in order to reach equilibrium. If our K again is 10, and our Q value that we've calculated is greater than our K value. So let's say maybe this is 15, maybe it's 20, maybe it's 25. It's some number greater than my K's value. What that means is that my reaction is going to have to shift towards the reactants to make more reactants in order to reach equilibrium. So your comparison of K to Q is going to denote which way the reaction is going to take place in order to reach equilibrium. So the way that I do this, rather than looking at 1, 2, 3 and memorizing that and whatnot, I always write my K number down first. Then I write Q as far as, or in relation to where it would be on my number line. So if Q is less numerically than K, then I write it on this side. And if Q is on this side, then I have to shift towards K, shift towards my product side. If numerically I find that Q is greater than K, then I write Q on this side, the right side. What's happening there is that numerically I have to shift to K. I have to shift to my reactant side. So this is an easy way to not have to memorize these little steps here. Now, part 2 says if Q is equal to K, all right, so let's say we found that K is equal to 10. Well, Q is also equal to 10. then we don't have to shift anywhere. We're at equilibrium already. So let's put this into practice with a couple example problems. So we're on exercise 8 right now. Let me scroll down and we'll go through these example problems together. So this first one says that we know the equilibrium constant, so that's K, is equal to 6 times 10 to the negative 2. And here's that key word here. Predict the system, how it will shift to reach equilibrium. That's the key word to know that we're going to have to use the K versus Q approach. So what I want to do is set up my Q expression. This is the synthesis of ammonia. Again, it's that Haber process, which is N2 plus H2. You should already have this memorized, is equal to, yields NH3. We have to put a 2 there and a 3 there to balance that equation. So this is the Haber process. It's the synthesis or production of ammonia. Well, now, what I'm given here, you see the little zeros right there? Those mean initial values. So again, the only thing that I can plug into Q expressions are initial values. Those are at time 0. So that's what I'm going to plug into my Q expression. So I plug in my Q expression. Let's write it out first. Always write a good expression. Don't plug it in any numbers. So NH3 squared over N2 times H2 cubed. Now we can plug in our values. So what I'm going to do is I'm going to take this value, plug it in for NH3, this value, plug it in for N2, this value, plug it in for H2. Make sure you square that, make sure you cube that, make sure you're multiplying those. And when you do so, you end up getting a value that is equal to 1.25 times 10 to the 7th. So that is our Q value. Now that we've calculated Q, we get to analyze and compare it to K. So like I said, always write your K value down first. So K is equal to 6 times 10 to the negative 2. Now, let's figure out where Q is in relation to this. This is to the positive 7. This is to the negative 2. So Q is greater than K, which is 1.25 times 10 to the 7th. So if Q is greater than K, which direction is my reaction going to shift in order to reach equilibrium? I'm going to shift towards K. So, because Q is greater than K, my reaction will shift to my reactants or shift left in order to reach equilibrium. And that's what I do to justify. So if this is a free response and I have to justify my reasoning and all of that, I would actually show my math here. I would show that my K versus Q, but just this alone will not give you credit. I have to explain this in words. So what I would say is that because Q is greater than K, your reaction will shift to favor the reactants, and that should give you good credit. So let's do B and C real quick and figure out which way we're going to shift. So since I've already written my expression down right here, I'm just going to plug in those numbers. And when you plug in those numbers, you end up getting a Q value that is equal to 0.06. So now we have to compare that to K. So again, I write my K value first, 6 times 10 to the negative 2. Then I say, all right, well, since this is a scientific notation, what would this Q be a scientific notation? Well, it's also 6 times 10 to the negative 2. So Q in this case is actually equal to K. So what that means is that there will not be a shift because Q is equal to K. So that means it's already at equilibrium. It's already there. Let's do part C together as well. So I'm going to use pink for this one. When I solve for my Q value, I end up getting 0.002. And all I did is plug these values into my expression there. So my K value is 6.02, or I'm sorry, 6 times 10 to the negative 2, my Q value is 2 times 10 to the negative 3. So where is that in relation to K? Well, Q is less than K. So what that means, because Q is less than K, my reaction is going to shift towards my products, to favor the products. How do we justify that? Well, because I show my math, I would say Q is less than K, so therefore my reaction will shift to favor the products. And that should give you good credit. So again, the only time when we have to use this is when we're trying to predict the direction in which a reaction has to shift to reach an equilibrium, because Q is not at equilibrium. So I hope this is helpful. I hope you can hear me because I'm stuffy and I can't really talk, and I'll catch you later.